Hello there, I'm Peter Chen. You've seen me in such fine quality chemistry educational videos as Percentage in Chemistry, Who Would Have Thought? And does CSI actually use percentage composition in chemistry? Today we're going to be looking at percentage yield. And in the idea about percentage yield, the concept is you run a reaction, you get a certain product. Now there's going to be two kinds of yield. A yield is something that you get, as opposed to yielding in driving when you let the other person go through and you got that triangular sign that's yellow and it says yield. This is a different yield because we're talking about yield in chemistry. But we need to talk a little bit about the formula, the idea behind the theoretical yield and the actual yield. Now the theoretical yield this is what you calculate on paper. This is what you calculate on paper. This is doing all the stoichiometry moves and the moles to moles and grams to moles and moles to grams and da-da-da-da-da. Then we have what's called the actual yield. The actual yield, you run the chemistry reaction, you run that chemical reaction, you do the chemistry, and this is what you actually got. So that's basically the difference between theoretical yield, that's perfect world, everything goes great, and it's on paper, and the actual yield is what do you physically get in your chemical reaction, your product that you are interested in. So now that we got those basic ideas out, how is this percent yield thing going to work? Well, the percent yield, there is a formula, and that formula happens to be the actual yield divided by the theoretical yield, and you multiply it by 100 to equal the percent. Now, why do you need to multiply by 100? Well, because if you take your actual yield in grams and divide it by your theoretical yield in grams, you're going to come up with a decimal. And that's going to be like, 0.67 or whatever, okay? But that's not your percent. You have to multiply by 100 to get your 67%. Or another choice that you have, if you have a decimal, you can move it over to the right two places, and that will get you the same results. Okay, so now that you've gotten the basic idea behind the theoretical yield, the actual yield, and the percent yield, let's go into a problem. We're going to go back, and here's our problem. What is the percent yield if 1 gram of hydrogen and excess nitrogen that actually yielded 10 grams of ammonia? Now granted, nitrogen is 14.01 grams per mole. We get that from the periodic chart. Hydrogen is 1.01 grams per mole. Once again from the glorious periodic chart. And here's our reaction. So this is it. This is what we got to do. Well, first off, we have to say, okay, excess. What is it about the excess? Excess basically means you have more than enough. If you don't understand the stoichiometry, here, do see another one of my other stoichiometry videos. Start working your way up, okay, so that you get to this point, because I'm going to assume you already know how to do the stoichiometry on this. Okay, let's look at it. Well, nitrogen is in excess, so yay! We can go cross that out. We don't have to worry about it. Now, we do happen to have 1 gram of hydrogen, and we need to know how many grams of ammonia that we are going to get out of this 1 gram of hydrogen. Now, I want to point something out. This, ladies and gentlemen, is your theoretical yield. This is the yield that you're going to work out on paper. That's the perfect world. Whereas, if we look over here, this right here, this is your actual yield. Okay? That's your actual yield, this is your theoretical yield. That's very important to make that distinction, because in our world we should not be having a 100% plus percentage yield. That would be, oh, something's not totally right. Okay, let's go. So, given that we have 1 gram and we have our hydrogen here, so we have to go from grams of hydrogen to moles of hydrogen. Okay? That's what we need to do. So it's like taking, here's this weight of hydrogen, how many hydrogen molecules do I actually have? And remember, a mole is such a giant number. So we go from grams to moles, we are going to need to divide. Absolutely. So 1 gram divided by, well, in this case, we're assuming 1.01 gram for 1 hydrogen. There's 2. It's going to be 2.02 grams, okay, of this stuff, of this wonderful stuff, okay? And so we have 1 divided by 2.02 equals, and we have 0.495, okay, that equals 0.495 grams, I mean not grams, 0.495 moles of hydrogen gas. All right, we got our first base. I kind of liken it in a way to baseball, and I've noticed that I put the view on, and for some reason, when I hit it, it's shrinking it. It's trying to show you the entire page, which that's not really what I want. I just want to show you the process as we're going through here. So now we have 0.495 moles of H2. Okay, wonderful. Okay, now what do we do? Well, we're going to have to go from moles of H2 to moles of NH3. This is what we need to do. We have to change the numbers of hydrogen molecules, hydrogen gas molecules, over to numbers of ammonia. That would be a pretty important thing. So, how do we set that up? You might remember a certain little formula that we came up with in class where we said the reactant of the equation over the reactant that's given is equal to the product that's in the equation over the product that we need to solve. Okay? This is a formula that would be easy for people to remember. And you can go ahead and plug that in. So I wrote that formula. Notice I wrote that formula in black to bring attention to it, because that would be the easiest way to do the mole-to-mole calculations. Now in this case here, we're doing it in blue. We know that for every 3 H2s, we're going to get 2 NH3s out of that. That was given in our original equation that we see up here. That's the ratio. So here we happen to have 0.495 moles of H2. How many moles of NH3 are we getting? Okay, that's the question. Remember, a mole is a number. It's like a dozen. I call it the chemist's dozen. So pay attention, because if we did the actual calculations with Avogadro's number, that 6.022 times 10 to the 23rd, we would be having numbers all over the place. Let's keep it simple. It's moles. That's what chemists do. That's what chemistry students do. Let's do that. So 3x is equal to, well, 0.495 times 2 essentially is 0.99. So x is going to equal 0.33 moles of NH3. Well, that's not a lot, is it? 0.33 moles of NH3. Okay? That's our blue step. Now we're going to go with, I like to call this the baseball experience. We went first base, here's second base with moles to moles. Now we're going to third base. In third base, we're going to go, we'll do that in black, okay, and we are going to go from moles of NH3 to grams of NH3. Now, how do we do that? Well, we have to multiply. What are we going to multiply? Well, the number of moles of NH3, and we're going to multiply that by how many grams are there in a mole of ammonia. Well, that we're going to have to figure out grams per mole. We know that we have one nitrogen, and that's 14.01. That was given to you in the problem. It's on the periodic chart. You have 1, 2, 3 hydrogens there, 1.01, 1.01, 1.01. Okay, and that makes it 17.04. We just add them up. We don't multiply it, we just add them up. Now, could you take the 1.01 of the one hydrogen and multiply it by 3? Yes, you could do that. So you're going to add that up and you're going to get 17.04 grams per mole. Okay? All right, so 0.33 times 17.04 equals. And I have, for my answer, 5 point, whoops, let me erase that, it doesn't look right. Okay, so now we're going to have 5.62 grams of NH3. We just finished third base. Now we got one last one. We're going to deal with the home now. We're going to deal with the home. Okay? Or, as they would say in Mortal Kombat, finish him! And that's what we're going to do. Except, we need to pick a color, and I gotta remember which ones we have. Okay, so we need to do it in red. I have to change the actual yield. I have to cut that in half. So that's really 5 grams of ammonia that we're looking at. So, our actual yield is 5 grams. I had to change that because I worked with a different number before I made the video. I worked it out with a different number. And in this case here, that's fine, it'll work. So our actual yield is 5 grams. Our theoretical yield is 5.62 grams. So now we have two numbers. One is what we physically got in the lab. One is that we calculated on paper. Okay, well, again, what's our percent yield? Well, our percent yield is equal to actual yield over theoretical yield multiplied by 100. That's what we have. Okay, let's take a look at it. Actual yield over theoretical yield. This shouldn't be too bad. So we have 5 grams over 5.62 grams, and we're going to multiply that by 100. Now remember, we have to multiply by 100 because if you just take 5 divided by 5.62, you're just going to get a decimal. And that's not going to give you the percent. And if you put the decimal down as your answer, I can't give you full credit. No teacher honestly can. All right, let's do it. 5 divided by 5.62 equals. All right, so I got 0.889679. Okay. What is that going to look like? Well, ladies and gentlemen, we multiply that by 100, and we're going to round it to 2 decimal places, so it's going to be 88.97%. And that's it. So our percent yield is 88.97%. It's 4 steps, guys. It's 4 steps, just like the 4 bases in baseball. Your first base, you have to take the grams of your reactant, change it into moles. We did that here in green. Then the second base, we took in blue. We did it in blue, moles of H2 to moles of NH3. Okay. Then in the third base, we ended up taking moles of NH3 to grams of NH3. Okay, and then the fourth base, sliding for home, ladies and gentlemen, we did the percent yield calculations. So we had to do those 3 bases of work before we could actually go and figure out the percent yield. Hey guys, I hope this helped you out. And in the meantime, enjoy. Take care.